tonight. Welcome everyone. My name is Amy Wright and I work for REP as the Regional Agricultural Land Care Facilitator. And we're pretty excited to have you online tonight with us to have a bit of a chat about soil acidity on Eyre Peninsula. Couple of quick housekeepings, which won't be too bad with the lower numbers online, but if you do have a question, please feel free to pop it in either the chat box or put your hand up and we will get to you as soon as we can. That would be great. So to kick things off, I'm going to hand straight over to Ruby Hume, who has just finished her PhD in the soil acidity field, and she's going to have a little bit of a chat to us. So take it away, Ruby.
Cool. Thank you very much, Amy.
You might just want to do screen sharing, Amy.
Yes, sorry guys. Now you should be able to go for screen sharing.
Thank you. Let me just figure out where I am here. If I go like that, sorry, give me a sec to get myself sorted. And then if I press that button, can you now see my presentation view? Yep, sweet, okay, cool. All right, so to kick things off, I'm just kind of going to give a bit of an overview of acidity, what it looks like, what causes it, and ways that it's managed, and then a bit of a situation of acidity on the Eyre Peninsula. So as Amy mentioned, I've just kind of finished with my PhD, which is kind of nice, and now I'm working for the Department of Environment and Water as a soils officer there. But I want to acknowledge as well that quite a number of these slides have come from Brett Masters, previously of PIRSA and SARDI, so shout out to Brett for those ones as well. All right, so when we're talking about soil acidification, we're speaking about soils that have a pH of less than 5.5 in calcium chloride, which on your field test kit is kind of that lime greeny colour. And it's a problem, or it's a naturally occurring process. So acidification happens over time, but it's accelerated in productive farming systems. So it's kind of something to keep your eye on if you've got if you're in an agricultural space, which many of us are. And it's an issue because it reduces the production potential of crops and pastures. And it's even more of an issue because it's becoming increasingly widespread internationally, in Australia for sure, and yeah, most definitely on the Eyre Peninsula, which is where we're focusing this evening. And so in terms of kind of like the area of acidity that we're seeing on the EP currently, the trend for soil acidity over time is definitely increasing. So you can see since 1999, the area of acidic soils has increased to about 234,000 hectares currently, and that's projected to increase into the future without any management. And you can see this green dashed line at the top here is the kind of potential total area that can acidify over time. So that's kind of worst case scenario. And in terms of like where that acidity is occurring currently, it's kind of two main areas. So we've got the lower Eyre Peninsula around Cummins towards Coffin Bay, which is an ironstone kind of loamy soil, so quite a sandy soil. And then also in the eastern EP, up just above Cleve, in those red-brown earths, which are also quite sandy and tend towards acidification pretty readily. And then moving kind of the next step from that previous map, we're looking now towards areas that are prone to acidify in the future if management kind of isn't undertaken. And so you can see here that the area of acidification is increasing quite significantly, and it's also extending into areas where it's not been seen before. So moving further south from Cleve and then across into the west as well, again in these kind of sandier soils. But it's kind of, if it's not managed effectively, it's likely to cover 19% of the agricultural land on the Eyre Peninsula. So it's kind of something to be aware of and to manage. And in terms of the impact of a soil acidity and why we need to look at managing it, there are a number of factors that are associated with soil acidity. But before I go too much further, I just want to talk about what this kind of acidity and pH is. I suppose fundamentally it's really the concentration of hydrogen ions in the soil. And so that's measured by pH. And just a note that I'm sure you've heard before, but I just kind of think it's easy to forget and it's really, really significant, is that the pH scale is a logarithmic one. So if you're moving from, a pH of 6 to a pH of 5, the soil is becoming more acidic, but it's becoming 10 times more acidic. And if we're then moving from a pH of 6 to a pH of 4, that's becoming 1,000 times more acidic. So it's kind of just like keeping that in the back of your head as you're moving through these numbers, moving forward. It's like a lot of acidity is occurring when you're decreasing your pH. And so when that pH does decrease, you start to see deficiencies in some of these fundamental nutrients. So magnesium and calcium and phosphorus are kind of some of the more familiar ones, the macronutrients that are necessary. And then molybdenum is another that becomes less available as soil acidifies, and that's really important in root nodulation. So that's when legumes really start to suffer in those acidic soils. And then on the flip side of that, in acidic soils, there's an increase in the availability of some of these less favourable elements, such as iron and magnesium, manganese, and most significantly, aluminium. Another thing to be aware of is in acidic conditions, microbes don't love acidity, so they kind of lose some of their functionality, so that the mineralization and those kinds of things start to drop off in really acidic soils as well. So if we look at what happens with aluminium in acidic soils, basically when the pH decreases, the availability of aluminium increases. And when that occurs, root growth is significantly affected. So we see kind of a stunting of root growth and deformation of roots, which basically means that plant access to water and nutrients is reduced. So you have lower crop yields as a result of that. And then if we are looking here, these are some samples collected from the Eyre Peninsula and looking at how pH affects the aluminium availability. You can see that as soon as we kind of reach this threshold point of 4.8, the amount of soil samples that have an increased aluminium availability significantly increases. So they're kind of now starting to increase over this critical threshold, which is where we start to see the roots struggle. Worthy of noting here, though, is that not all soil samples are affected by this aluminium increase, because not all soils have aluminium in them. So you need to have that aluminium present in the first place to really see the effects of aluminium toxicity. And another thing to consider is that not all crops respond to acidity in the same way. Some are more vulnerable and more sensitive than others, and that's particularly those kind of legume crops, like I mentioned before, in terms of the way that they nodulate and the way that they nodulate and the way that they grow in acidic soils. It's reduced in acidic conditions. This is a picture of the chickpea down here. So it's quite clear that in that acidic soil, the chickpea is struggling in comparison with an alkaline soil. That's a similar case for other legume crops like lentils and fava beans and things like that struggle. There are some species rather that are more tolerant, but I suppose the more a soil acidifies, the harder it is for a plant to grow. So you can kind of reach a point at which all crops are going to struggle. And just a little bit further on that nodulation point, this is some data that's come from Helen Burns in New South Wales. But it is just looking at kind of number of root nodules as a result of soil pH. So you can see here, as the pH decreases, as the acidity increases, the amount of root nodulation also decreases. So that has a significant effect on the access to nutrients. And then in terms of soil acidification, I mentioned that it's a naturally occurring process, so it's something that will occur over time, but it is absolutely accelerated in these agricultural systems. So this picture really nicely demonstrates that, kind of two soils that are the same fundamentally, but it's just the way that they've been managed here. And you can see that the pH has started to decrease quite significantly through that soil profile. And as a result of that, the aluminium has also increased. And so in terms of kind of what is causing this acidification in these agricultural systems, there's a number of different factors that contribute. One of them is kind of this product removal. So I suppose what this diagram is demonstrating is that a plant is by its nature kind of an alkaline thing. So if we if that plant were to grow and remain in the system, die and decompose within the system, that alkalinity from that plant returns back to the system. But as soon as we start to harvest that and take it away from the system, that's when you're removing alkalinity from the system, and that will cause an increase in acidity within that soil system. And then beneath the surface, another kind of thing that is happening down below is that as plants are taking up nutrients, the majority of the nutrients that they're taking up are cations, so they're positively charged. So the plants are taking them up into their roots. And to maintain the balance in the soil, the charge, they need to exude positively charged ions back out to keep that balance aligned. So they put out hydrogen ions into the system. As I mentioned, acidity is just the concentration of hydrogen ions. Putting more hydrogen ions into the system increases the acidity. And then another factor that's also contributing is the nitrogen fertilizers that are being applied. So that can happen in a number of ways. I suppose if we look over this side here at the ammonium-based fertilizers, so the urea, the sulfate of ammonium, those kinds of things, they transform into a nitrate to be plant available. And in that process, as the ammonium turns into nitrate, a number of hydrogen ions are released. So again, that's that acidifying process taking place. And another thing that can occur is if this nitrate, whether it be from ammonium or directly from a nitrate fertilizer, if that's not all taken up, that can leach out of the system, and that is another acidity forming factor. So there's kind of a whole number of different things associated with fertilizers that can increase the acidity in that system. And then if we're starting to look at kind of which fertilizers might acidify more, this graph is basically showing us per bag of fertilizer, how much lime is required to neutralize the acidity that's caused by the fertilizer. So we can see that some fertilizers require less lime, some require more lime. But I suppose in terms of two of the kind of most commonly used ones, that's that urea and the sulfate of ammonia, what the message to come from this slide is really that the sulfate of ammonia needs more lime to kind of counter for its acidifying potential than does urea. And the reason behind that is simply because you need to apply more sulfate of ammonia to give the system the same amount of nitrogen as you would with this smaller amount of urea. So that's kind of a sense of we need to balance out the acidity by adding lime. And that then moves us towards some of the more specific kind of estimates of soil acidity and lime use on the EP. So I've mentioned the word lime quite a bit already, but it's really just the most kind of common and definitely in Australia, one of really the main way that we remediate acidity is with the application of lime. And so I'll just quickly mention there are definitely other materials that can be used in place or as well as lime, but for the purpose of today, we're just going to be focusing on that lime, that calcium carbonate. So going here to the area of soil that is acidic or potentially acidic, you've seen this figure before. What this graph on the right-hand side is showing is basically the amount of lime that is required to neutralize that acidity that is arising. So we can see that kind of we're here with the 234,000 hectares of acid soils at the moment, and that is requiring 40,000 tons of lime to be able to remediate that acidity. And as our acidity increases, so too does our need for lime. We compare kind of the requirements to balance out the acidity with now the actual lime that has been used in the EP since 1999. So this is showing again in thousands of tons of lime per year what's been applied, and it's kind of been hovering between 1999 and about 2015, 10 to 15,000 tons per year, and then we see this dramatic spike here. And that's likely due to a number of different reasons. One is the opening up of a new lime pit, and I think a reopening of an old lime pit as well. Which has made lime more available and so cheaper and more easier to access. In combination then with the availability of Verus mapping, so pH mapping of paddocks, just providing growers with more information about where acidity is in their paddocks and where lime is to be applied. And then kind of outreach and webinars and information like today, just providing people with more information about acidity, the problem of acidity, and why it's really important to fix it. So we've seen lime use has definitely increased. We look at here this graph of what lime has been applied versus what lime is needing to be applied to kind of remediate this acidity that's arising. And that allows us to get a bit of a kind of a lime balance, or like a lime catch-up rate, to ensure that all of that acidity is actually being remediated with lime. So what the next figure is showing us is the cumulative lime balance. And basically what it's saying is how much the soil is acidifying versus how much lime is being applied. We kind of add those two things together, and this is showing us what the lime deficit is, or how much more lime needs to be applied to kind of cut even, I suppose. So you can see in the initial few, those first, 25-ish years, lime was being applied, but it simply wasn't enough to keep up with the rate of acidification. Around here, where that big spike of lime application occurred, some of the kind of recovering some of that deficit, I suppose you could say. But the overall take-home message is that the system is still in a lime deficit. So acidity, there's still more acidic soil than there is lime being applied. So I suppose as much as that nice big spike in the previous graph shows that it's heading in the right direction in terms of lime use, this graph here is just really demonstrating that there's still a way to go in terms of catching up with the lime. And that's not factoring in kind of future acidification. So that's probably likely, this number is likely to be quite a bit greater than that as well. And so I suppose that's kind of me for the moment, just in the sense of where we're at, what's happening, what the problem is. And I might open up for a few questions if there are any, but if there are not, we'll shoot straight across to Josh.
Thanks for that presentation, Ruby. Do we have any questions from our audience tonight? No, doesn't seem like we do. If you do have any questions throughout the talk, guys, please just pop it in the chat box and we will get those answered. I will now hand over to Josh Telfer. He's going to do a bit of a presentation on the monitoring and surveillance site program that's been occurring across the EP for quite a number of years.
Guys, again, thanks for joining us. And this comes on the back of a city forum we had earlier in the year with Ruby. And this part of it is about some monitoring sites right across southern and eastern Eyre Peninsula, where over up to 13 years, some sites have been monitored to look at acidity. And I just wanted to pull apart a few of those tonight and just look what we can learn. And the insights really into how we manage them going forward and what effect lime has had on these soils, so we can really track them over time. Like Ruby said, I really want to acknowledge the work that Brett Masters has done over the last 13 years. He started in various projects since 2010 looking at tracking this soil acidity. And in 2010, they had a whole big project right across Eyre Peninsula. They looked at 66 different sites, and they're obviously looking in acidic areas, but 67% of the sites below the target in the surface. And then if you go below the surface, it was 23%, but even then we're below the 5 level, which is getting pretty low. But of those 66, 35 of these sites have been monitored since then, both in 2010, then 2013, 14, 19, 20, and now just in 23. And so looking at these Valiant sites, it's really been able to really get into what's been going on, what's happened when lime's applied and when lime's not applied. And we also get a sense of how quickly they're acidifying and how quickly they're chewing through that lime. And these are the rust figures that they've generally come up with in the higher rainfall areas. We can go through 80 to 200 kilograms per year. Obviously, we're not encouraging to apply that every year, but in the whole balance of your particular farming systems, these are the kind of numbers that the monitoring sites are suggesting. But over the last 10 years, also, there's been an increase in cropping intensities and improvements in yields, and full credit to the farmers who've done that. But like Ruby was saying, any time we take material out, we're going to increase acidity. And any time we apply mineral fertilizers, we're going to push that line as well. And different soils will naturally buffer this at a different rate. And so the ones that don't buffer it very well are the first affected, and they tend to be sands and gravels. And certainly lower EP has plenty of that. But you will see a bit later, sometimes that's a good and bad thing, because if you get more heavy clay soils, they'll take longer to acidify, but they'll actually be a lot harder to treat because they'll change back up so slowly. So there, in 1920, these were resamples again, and we adjusted our targets for those. But still, 50% of those 35 sites we still had subsurface layers that were below that critical value of 5. And that tells you a bit about what's going on. So when you apply lime, obviously 99% of it goes on the surface. And so if you've got acidity at depth, well, then there's a lag between that moving to the subsurface, but also while it's in the surface and the surface is acidic, it's reacting with that too. So it's chewing through some of the lime as well. And the other important thing that happened, particularly interested in someone like Billy, is there were 20 additional sites established in this project in the 1920 area, which are sites that aren't particularly gravelly or sandy or wouldn't have traditionally seen acidic soils, but they're light textured, often siliceous sands that farmers are getting amazing yields on, and they're really pushing them hard and applying lots of nitrogen. And so we're a bit like Ruby's map saying there's these potential areas. We really wanted to get a sense of what was happening with these soils before they got really acidic. So we really set up an extra 20 monitoring sites to look at sites that we didn't think were acidic, but all the maths and the science around it said that this could really happen. So it gives us a good canary in the coal mine effect to really look at these and see what's happening. So those that know Eyre Peninsula, which is, you'll see a cluster down. Can people see my mouse pointer? I'm not sure. Cluster down the lower EP in yellow, and then a cluster in yellow up the top on Eastern Eyre. And these are the areas that traditionally would have been the target for acidity workshops and people going, we know the science is quite clear. We need to add lime for these soils. But then you'll see the purple sites that cluster right through. These are the emerging sites I was talking about. And as Billy would know, right out onto the western side of the lower EP, there's quite a lot of lime. You're near the Bight, and there's quite a lot of traditionally would have thought calcareous soils or siliceous soils, but these are being monitored because we know that it's not all like that, and they are being aggressive, sounds the wrong word. They're being intensively farmed right across through to Warminda, and they've got a couple of sites up around Lock as well. And we really wanted to have these as the canary in the coal mine to really give us a bit of an understanding what was happening in these soils before they were all that, if they were going to go acidic at 4.5, because all of a sudden this becomes an even bigger problem. So they haven't got quite as long a monitoring history. They only go back to 2019. But I'll show you some interesting data. Even these soils have been seen to move. So it really gives us a bit of a heads up to know that we need to start actively managing these going forward. Is there any questions for a minute?
I think we're right at this stage.
So this year we've resampled both the 35 existing sites and what's called the 20 emerging sites, which is those sites in the traditionally not, the city wasn't a big concern. And I just want to draw out some of the learnings from these. And the big difference is for the sites that go back to 2010, they were traditionally sampled at 0 to 10, 10 to 20. So quite a coarse sampling. And then when the newer sites come on in 2019, there was a sense that the best practice was probably to get small increments. But one really interesting thing we did, because historically they were done at 10 and we were going to do the project at 10, we thought, well, actually, it'd be really good to update those increments to capture what's going on at their smaller increments. But we also wanted to be able to relate it to the historic data. So we actually sampled both intervals. And I'll show you a bit later, that's actually become really a useful comparison, because we can see what we're missing with that coarser sampling. And most nutrition sampling you'll get when you collect available P and other things is in that 0 to 10 sample. And we look at pH at the same time and think, oh, well, is it good? Is it bad? Is it okay? But by going to that narrower sampling, you can really find out a little bit about where that lime is and also what the soil is doing. And I'll delve into that a bit later. And of all the sites in 2019, this is sort of where they fell. We had a percentage in the 4.5 and 5, and you can see there is still quite a wad of subsurface stuff, because a lot of these sites, when you tell farmers that you're monitoring the pH, they think there must be problems. They go out and spread lime. So there's a lot of these have been treated with lime, but you can still see this telltale sign up here. There's quite a lot still of subsurface acidity. And some unlimed sites really measured the acidity layer. It's moved in a couple of years. And this is the similar shot that Ruby showed, just that there's been a marked change, all credit to EP farmers, of lime applications from that 16, 17. It tripled and then it doubled again. So this has been a combination of things around pit availability, reduced freight costs because the pits have been in different areas, but also really a push to upscale in that higher value legumes. And I know Billy knows that's the space he lives in. Can they take lupin country, which you saw from the plots from Ruby, is quite an adapted plant to acidic soils, but it wasn't a really high value crop. So people are going, can I grow a higher value legume by investing in my soils? Wheat, funnily enough, which is obviously the mainstay of EP, is really, really well adapted to acidic soils. So oftentimes you don't get a big whack extra yield for managing acidity with wheat per se. But having said that, everything else works better. So if all of a sudden you start having better legumes, you'll end up with better wheat. And if you've got better roots all round, you'll end up with better plants as well. And if you end up with better plants, they can compete better against weeds as well. So it can be really you're treating the system as much as a particular crop. Now, just jump into some soil profiles here. This one here is actually not had any lime. So right from 2010, you can see this starts off around 5, which you might think is too bad. But as you get down to these subsurface, it's sitting at 4.8, which isn't that great in 2010. Fast forward to 2014 and 2019. I don't know what happened there. It should have generally gone down. But by this year, you can see at the surface, it's 4.5. And the subsurface, it's right down to 4.3. And that is seriously a low pH soil. And that's where the aluminium starts coming out of the soil, and really it's quite hostile to plant root growth. And then you end up with a plant that doesn't grow very well because it doesn't have very great roots. Further up north, here's another scenario where there's nil lime, and this is quite a heavier soil compared to the last one. This one's it's described as a shallow sand over poorly structured clay with ironstone gravel in it. So it's really good at moving water through the profile, and that washes out. So it acidifies quite quickly. This here is quite a heavy loam, and so it doesn't move water through it very quickly, and it acidifies a lot slower. I think, oh, that's great. Well, yes, in 2010, you wouldn't have had to worry about it at all. 5.8 or something, and we had an alkaline, probably 6.8 at the subsurface. Not a problem. There's been an explosion in cropping and intensification in this area up in the Cleve Hills. And every time we've monitored it, well, I don't know what was happening in 2019 again, but we've seen a definite trend towards more acidic conditions. And you can see right now, acidity would just definitely be affecting the soil. And unfortunately, these soils in the subsurface, because they're quite tight clays, it's really hard to meliorate this area here down in that 15 to 20 zone, because you've got water doesn't flow down there, but also lime will be chewed up in the surface as well, and it really does require expensive incorporation. So in perfect hindsight, we would have rather treated it back in 2010, just the surface, and we wouldn't have had this effect on the subsurface. But yeah, unfortunately, hindsight is not always useful as your heart. And this example here is probably more example of a low lime rate. So again, this is in the Clevefields, but it's a coarse sand. So you can see on the left-hand side what the profile was like in 2019. You had a little bit of acidity in the surface, but you had quite purple colors in the subsurface, and it was still quite alkaline in 2019 and 2010. But fast forward to, and the farmer has applied lime, 0.5 ton in 2015, and then he put 2 tons on in 23, although this is right as we were sampling, so it really hasn't probably affected the samples at all. But you can see that 0.5 ton in 2015 was essentially all chewed up on the surface. So the subsurface continued to acidify. This is the scenario in the Copiah Hills, and it has had lime, 2.5 ton in 2011, just after initial sampling. You can see the surface has come up, but that hasn't been enough. And while the surface has come up, the subsurface is actually worse off than it was in 2010, even though it's been limed. So this would be a case of under applying of lime has just not dealt with all the acidity that's floating around the system. And again, if you just sample in that 0 to 10, you might think you've dealt with it, but the subsurface is really coming. And that's the focus of my next slide. You'll see that subsurface is really starting to become an issue, particularly with no-till, and we don't have a lot of soil mixing. And when you're returning crop residues in the surface, that does buffer the soil itself, and doesn't get away from the surface, and you don't have a lot of mixing with no-till, and that's great for a lot of things. But oftentimes it's left the subsurface particularly exposed. And as I said here in red, that 0 to 10 sample doesn't always pick that up, because you're taking stuff that on the surface might have had lime, but that 5 to 10, it might be quite acidic. And if you mix those two together, you think, oh, well, that's nice and average. But unfortunately, where we need a lot of crop roots want to grow is that 5 to 10 zone, where when the surface dries out, they need their roots there to work really well. Just so happens that can be quite an acid choke. So if you're missing that through bulking soils from 0 to 10, well, it can be a real costly thing, and you need to know what's going on. But particularly in these sensitive crops like beans and lentils and barley, and dry years, you need every root to function. And particularly with the heavier textured soils, like I said, it takes longer to move down. You need to start looking at strategic tillage to try and move lime further into the soil at a faster rate. And Ruby might touch on that a bit later. I'll certainly demonstrate the more sandy, gravelly soils. This can happen just through farming natural processes, but don't just assume it's the case. This is a really good example of that sampling problem. We've got sampling in 2014 and 2010, so you can see, was it 4.9 probably in 2010? The farmers applied lime, nice increase. And yes, we can pick up subsurface here, but hey, we're treating this surface quite well. What's going on here? This blue line here is what happens if you sample at 5 cent increments. All of a sudden you realize you've made the surface quite, well, relatively alkaline, but only at 5 centimeters, we're at 4.6, and that's not very far down. And if you'd used conventional sampling at 0 to 10, you would have totally missed that you had this massive issue just below the surface. And so really encourage people, particularly once you start liming and you start adding lime to the surface, you really need to be at that 5 cent increments, particularly in the top 10 centimeters. Less of a problem as you get deeper because everything's a bit slower, but in that top 10 centimeters, you really need to, 0 to 10 is just far too coarse and it will be misleading. Again, this tells a different story of this this increment difference, because the orange line would be the conventional, and we've got, it's not quite so bad, and we've got a reasonable amount of lime input. We've got 3.7 tons over 6 years, and this is quite a coarse sand, so the sandier soils naturally will react faster, and also there's less acidity. Because acidic pH is measuring the concentration in the soil water, there's more sites to engage on a clay, so it chews through more of the lime, if that makes sense. So sands go down really quickly, pH, but they're also a lot easier to bring up as well. So again, this is probably impact of underliming, and quite a heavy textured soil here as we, so this is the sand has come up, but the subsurface is continuing to acidify. And again, this has had quite a decent lime rate, and this is in the Cleve Hills, and you can really see we've actually been able to, because it's sandy on top, it's described as a red sandy loam over clay loam. We've actually been able to move that, not heaps, but we've been able to move that pH a little bit up, and then it's actually affected the subsurface, which is a really good outcome. But if you look at if you increase the sampling intervals, well, yes, the surfaces have gone even better. It's back up to where it was in 2019, but it's still low in the only just off the surface, 5 to 10 centimeters. So that tells you a little bit about these traditional sites. I want to talk a little bit about these emerging sites, because they are really interesting, and like I said, it's a bit of a canary in the coal mine as to how these have responded. And this is a site near Ongara where they started, like I said, one of the incentives to grow lime is to grow beans, and they've really seen with these lighter texture soils, you can really get a response. But before it was limed, when it was monitored in 2020, we were definitely seeing effects of salinity, of acidity, at 4.5 in the surface, and just below the surface even lower. And as the surface has responded, we've still got this acidity that sits 5 to 10 centimeters. So it's certainly not totally fixed by any means, but it's definitely better having this at the surface. Getting a bit closer to you, Billy, this is at Karku. Not terrible pHs at the moment, and it's had 2 ton of lime. So it's sort of one of those monitoring sites. Glad everything's not bad. And also just want to, this is a bit of an introduction to some of Ruby's stuff, because we've had sites we've monitored, and we want to know of the lime we put out, how much it actually is still there. Because if it's still in that lime phase, well, it won't change the pH. It's actually got to dissolve with the acid to engage with the soil acidity. So the question is, of all the lime you put out, is there still some left unreacted? And so some work that, it's cutting edge stuff that Ruby's done. She's really started to pull apart where stuff is. And I've got some sites here where there was quite a reasonable lime history sometimes, and this probably surprising how little actually is left. It's a comparison, some sites. If you look at, is at Copio, Copio and Coccolici, there's quite a variation in terms of how much lime, the pH down the profile. And this is similar to the plots we'd seen before. but also how does that interact then with the lime that's in the soil? And if you see here, this is some work that Ruby's done. Even though we've applied some lime, say in E, it's almost nothing left. And even these values here, Ruby will say it's not very much at all. So we are certainly dissolving the lime we're putting on. But it does mean there's no big wad of magical lime that can come out of the soil and keep reacting. It's really an incentive to keep applying lime. But I just wanted to, go, because I think there's still things that can be used in these monitoring sites, because it does give a snapshot of what's happening with the soil over time and how quickly things are changing. And we can measure and estimate how much nitrogen we're putting on, how much crop residues we're taking out, and it really gives us a sense of which particular factor is really driving acidification. And it appears that it's this nitrogen fertilizer has been the real particularly on the sands and gravels, real issue that has really driven acidity to react. And farmers, to their credit, have seen this and really stepped up and started applying a whole lot more lime. But unless we get this data, we want to provide support for the farmers to say you're doing the right thing, or you need to keep this up. I'll just backtrack because I think I've missed one slide I wanted. Oh, this scenario here, I somehow went over it. So this is probably the best case scenario here. You've got a sandy, a loam, limestone loam, and this farmer has actually applied 3 different applications of lime over the last 10 years. So he started in 2010, quite acidic. So he was at between 4.2 and 4.3. Down the profile, and even at 20 centimeters, it's still quite acidic at 4.8. So he's banged in 3 different lots of lime at 2 to 2.5 tons. And you can see the site has really responded nice and evenly. This is the best case scenario. And you see there's not even any differentiation with this mod is the 5 centimeter increment sampling. I wish it was this easy for all the sites, because too often it's not like this. It's more like this with stuff not moving down and whatnot. So I really encourage people, if you're interested, if you think your site's affected like this, reduce your sampling intervals, because it gives you a lot better accurate idea of what's going on. pH testing isn't expensive. It's about $15 a sample. So even if you do 3 per site, it might be $75, but you give a really good, clear indication of what's going on that site. And if you record the location on your phone, you can go back there in 5 or 6 years and go, is this still, have I really improved this? And I think 5 centimeter increments give you good confidence that what you see is what the plants see as well. If there's nothing else, I'll probably over time, so I'll finish there. And if there's any questions, or I can wait to the end.
Thanks for that, Josh. That was a great overview of our where our monitoring sites on Eyre Peninsula are sitting, and hopefully there's something will come up and we're able to continue that monitoring as well. That would be great. Do we have any questions from anyone, Debbie or Billy? If not, I'm sure you're saving all your good questions for the end. Oh, Billy, you have got someone. A question. Josh, any sites on Lower EP that have had 10 tonnes a hectare over the last few years that you guys have monitored?
Not in these. These are farmer managed sites. So we've only gone with what they've done. That one I showed you at Lily, that's probably, now that's probably only 7 tonne. That's probably about as high as we've got. Ruby's got a little bit of data from the mid-north of ton applications of 6 tonne. There's quite a good reasons to add small amounts, because if you add 10 tonne at once, you can push this scale, a bit like I said, you can affect the surface. If you put the surface at after 10, you might go right up to 7 or 8. You actually need a little bit of acidity to dissolve that lime over time. So it seems like smallish. I wouldn't say 2.5 tons is insignificant, but these increments of that about a month every couple of years is probably a good way to do it. Yeah, there would be more research trials with higher rates, but probably not at 10 tonnes on EP. That might be some elsewhere in the state.
I suppose it also then just comes back to capacity on farm as well. I mean, you only, you can only spread so much at once, and I guess you'd only have the ability to focus on a smaller area if you're applying quite often.
Yeah, and it seems to be that while this is what farmers tend to do logistically, rates of 2 to 3 tonne, that actually works better with the soil anyway. And you're going to cause more issues by putting 10 tonnes on than your fix.
Yeah. Thank you for that question, Billy. And thanks, Josh, for that presentation. We are going to hand back over to Ruby to have a bit more of a chat to us around. What are you talking to us about tonight, Ruby?
I'm going to go back to some of the PhD work. So
that's right. So some of her most recent research, which is very interesting. So take it away, Ruby.
Thank you.
You'll be able to share into the screen now.
Okay, yeah, I'm just trying to. Can you stop share? Sorry.
Let's try it again. Can you see my screen now or not?
Yeah, good to go.
Okay. All right, sweet. Okay, so the second part of what I'm presenting you with today is more of a kind of research focus. So this is kind of the new stuff that I was doing over the past 3 years, looking at ways that we can apply new methods to manage acidity. And so that work, just checking when I press that button, you can see the next slide. Yep, sweet, cool. So the work that I was doing as part of my PhD was part of a much larger project with heaps of different people involved. It was really led by Brian Hughes up at Nuriukpa, but had a number of different people, and there are a few trial sites on the Eyre Peninsula as well. But that project was looking at new ways to manage this whole subsurface issue. So obviously Josh has touched on that and showed how significant it is and how difficult it can be to treat. So they were really looking at ways to kind of target that subsurface layer in the soil. And if you're interested about the project or about finding out any more information about this topic, the website here, acidsoilsa.com.au, has heaps of good resources and case studies and stuff like that, just to check out and dive a little bit deeper. And so I suppose there's kind of 3 components when it comes to dealing with acidity, and I've touched on all of them, but really the focus of my research was kind of this final monitoring stage. But I think, I'll mention the first 2 because it kind of all forms pieces of the puzzle. And some of the stuff that I say is reiterating what Josh has already said, but I don't think that's a bad thing. I know I personally need to hear things a couple of times to really get them drilled in. So there's some really important points to be made, I think. I guess this is just this point about acidity and soil pH being a hugely variable thing. So if you've had your paddock mapped, you'll understand how variable that pH can be kind of across on a spatial scale, kind of more horizontally, I suppose. But also really significant, and as we've seen with Josh's work, it's also hugely variable down the soil profile. So it's really, really important, in case you didn't get that message from Josh, that we're measuring at these smaller intervals to really identify those acidic layers. And this is just literally another slide just to push that point. So what I wanted to show here particularly is this soil profile here. If there is that stratified acidity layer beneath an alkaline layer and we sample it all together, as Josh has said, you miss the problem. So like if you take anything home from this whole session tonight, sample at smaller intervals to really get an understanding of what's going on in your soil profile. So that's kind of the whole measuring side of things. When it comes to managing, so the liming approach, I suppose the work that was happening as part of the larger project that I was a part of was looking at different ways of liming to really target that subsurface layer. So there are a number of different approaches that were trialled so there was about 15 trial sites across the state, which looked at kind of different lime sources, lime rates, and lime incorporation methods. So some of them were kind of just standard surface application. When I'm talking standard in our trial sites, that was from 2 to 3 tonnes per hectare, was kind of like the low application. There was also an increased rate at the surface. So this was moving up more into that 6 tonnes. There was 1 or 2 sites that had 8 tonnes per hectare. This is applied directly to the surface. And then the final one was that incorporation of the lime into those subsurface layers, kind of with the hope that getting it straight into those subsurface layers would help to speed up that remediation process further down the soil profile. Now, in terms of monitoring now the effects of this lime, as we've seen from the previous set of slides and of all those monitoring sites, when we measure the soil pH, that gives us a really nice understanding of what has happened to the lime when it's dissolved and when it's worked to push up the pH. But there's a whole kind of extra piece of the puzzle that was missing prior to kind of me coming on this project, I suppose. And that was about the lime movement and the measurement of the undissolved lime. So that's lime that's still sitting in the soil profile, hasn't yet reacted, so hasn't yet neutralized acidity, and so was available to continue to neutralize acidity into the future. And so that was kind of what we were really interested in exploring further, to see if we could find that information out and find a method to really help us measure that in the soil. I suppose, again, yeah, not only would it tell us about where that undissolved lime had moved, but it would also talk to us about kind of how much lime was left, and so if reapplication was necessary. So that was kind of the focus. And so the first question that I was trying to answer was like, is it actually possible to detect this undissolved lime in the soil profile? Because that was something that hadn't really been done, or the ways of doing it were quite complex and time consuming. And then after answering that question, or kind of building upon that question, we were then looking at like, can this help us to understand if and where the lime's moving, if and when reapplication is required, and then how much is needed based on the pH change and the amount of lime left in the soil, where it needs to go, and kind of putting all of those pieces together, can that improve the way that lime is applied in the future? Okay, so this is again banging home that same point. The more spatial resolution that you have, the smaller your increments in soil sampling, the more information you have about your system. Higher resolution leads to better information and potentially better decisions, I suppose. So for the sampling and the work that I kind of did in this method development space, we were sampling at 2.5 centimetre intervals. So I understand that that's quite labour intensive. So we kind of say 5 is fine. If you're really eager, go for 2.5, absolutely, and see what difference you can get. I mean, yeah, go for it. So that was kind of one of the things with sampling at those smaller intervals, a lot of soil samples to manage. And then the second thing was we were looking at these agriculturally relevant concentrations of lime. And what I mean by that is detecting really, really small amounts, kind of less than 0.5% of lime in the soil, given that we're hoping that it's moving through, so it's becoming less concentrated as it moves through the profile. And also if it's getting used up, that concentration is decreasing. So in order to really understand what's going on in terms of that kind of undissolved lime, we need low concentrations and we need high spatial resolution. So to get those two measurements using kind of traditional techniques, it's called a calcimeter, measuring small amounts of carbonate in soil, can take up to an hour per sample. It's quite expensive, it's super time consuming, obviously, and it's very labour intensive. So we were kind of looking at alternative ways of measuring lime in soil. And that was where this idea of soil spectroscopy came into the picture. So it is a cheap, relatively effective and quick alternative to traditional methods. And so when I say kind of quick and effective, it can be, spectroscopy can happen in a number of different ways. There's different kind of approaches, but the most simple, I suppose, way, you can literally go out into the field and scan a soil with basically no sample preparation at all. So that's kind of where the speed comes into the picture. And then you can take multiple scans at a time, get a whole lot of different information about lots of different properties. And that's where the cost effectiveness comes into play. So not only can we predict lime, we can also predict soil pH, soil carbon, soil clay content, a whole number of different variables from a single scan. And so we knew that this method was able to detect carbonates in soil, so that's the kind of the lime, but it wasn't yet clear if we could get down to those really low concentrations. And so that was really where the work that I did came into play, to kind of push that limit down and get low concentrations. Okay, so really briefly, I just want to give it a bit of an explanation about what spectroscopy is and how it works, to kind of just help fill out this picture a little bit better. So at its most fundamental, it is simply the interaction between light and matter. So as our eyes look at these 3 soil samples in the bottom of the screen here, we see how visible light is interacting with them differently, and we're kind of observing that in the different colours. And so that same principle is applied when we scan these soils with a spectrometer, but it's actually quantifying that interaction between light and matter now. And it's doing it at a slightly different wavelength from what our eyes can detect. But we measure that and present that information in a spectral signature that looks like this. And so you can see each of the different colors is associated with each of these different soil samples. And you can almost treat this signature as like the soil's fingerprint. So each one will have its own slightly unique signature. And within that signature is a whole lot of information about the soil chemical properties. So we can get a suite of different information from this signature. And so that was kind of the premise or the theory that I was using to develop this technique of lime detection. I'm not going to go too much into the steps to get there today, but all I will say is that we scanned a number of different soils with different lime concentrations and kind of found these zones here that linked up really nicely with the amount of lime in those soils. We ran some computer modeling and kind of a whole number of different things, which I won't go into today. And we're able to get this regression model, which is basically comparing on the y-axis what a spectrometer, what this signature can tell us in terms of lime concentration versus what the traditional lab methods, this is this kind of upwards of 1 hour per sample, what that method can show us. And so basically this graph here shows up that the two methods line up really nicely. So we can trust in the fact this new methodology is giving us an accurate representation of the amount of lime that's in these soils. And that was great. We wrote that up and that's a paper, and it's now actually, this method is hopefully soon becoming something that will be commercially available. So if you're interested in sending your samples to get kind of analysed to find out how much lime is available in your soils, it's on the horizon pretty soon, which is nice. So that was kind of step one, method that works, sweet. In terms of then actually applying that to look at lime movement, I went out to some of these trial sites that have been established as part of our larger project and measured the soils at 2.5 centimetre intervals and measured a number of different treatments. So we had different lime rates, and some of those treatments were incorporated and others were just applied at the surface. So yeah, 2.5 centimetre intervals, scanned them with the spectrometer, got those spectral signatures, ran my predictions, and then was able to get the carbonate or the lime presence through the soil profile. I mentioned here as well, previously that that squiggly line can give us a whole lot of information. It can also tell us the pH of that soil. So I actually also predicted the pH of these soils using that same method. And I suppose just to give you a sense, like one scan takes maybe 3, maybe 10 seconds to do. From that one scan, I can get a whole suite of different properties versus 1 hour for the lime and, you know, half an hour to a bit more for the pH. So we're saving a lot of time by using this method. And these are, so I'll just give you one set of results from these trial sites just to kind of give you a sense of the information that was available. And then I'll jump onto the Eyre Peninsula specific sites, which you've already kind of seen, but I'll go into them into a little bit more detail. So this is a site this is from Spalding, this site, so up in the mid-north. This pH graph is something that you'll be familiar with. This is again telling us about what has happened to the lime that's already been consumed and dissolved to increase the soil pH. And these are the responses that we're seeing in terms of that soil pH, basically. So the higher rates, the 6 and the 8 tons, have all definitely increased the pH in the surface. Where it's been incorporated in these darker lines here, that increase in pH is starting to work deeper down into the soil surface. But where it's only been applied at the surface, you can see that there's not really much pH change in comparison with the control soil. Now, the extra piece of information comes in when we look at the amount of undissolved lime. So this is lime that's still sitting in the soil, not yet reacted, will still continue to increase that pH over time. And so this is what we saw at this site. Again, there's still quite a bit of lime hanging out in the surface. So kind of links in with what we're seeing in the pH, but this is now the stuff that's not yet dissolved. So all of those higher rates of lime have quite a bit of lime left in the surface, and we see again that the tilled treatments, there's a bit of lime hanging out, and this is only at now 5 centimetres. So there's no lime, no undissolved lime present beneath 5 centimetres, and that's even when lime has been incorporated to a depth of about 10 centimetres. So I suppose what that's telling us is that the lime that was incorporated has been used up straight away to increase the pH. There's none left to continue to increase that pH with time, unless some of this lime up higher starts to move down. presenting this information slightly differently now. I think this kind of, for me and maybe for you, gives a bit of a visual about kind of where the pH change needs to happen and then where it can happen. So this graph here is showing us the amount of pH increase that is required at each of these different treatments to get a pH of 5.5 the entire way down the soil profile. Now, I've not included the control, so like if there was a red line in here, it would be up quite long for all of these different depths. But basically, it's saying there's, a pH of 1 is required in lots of these depths to reach a pH of 5.5 the whole way down the soil profile. And then next to that, what I've done is I've calculated, kind of based on the amount of undissolved lime that we could see in the soil profile, how much of a pH increase is actually possible if that lime were to be consumed to increase the pH. So what this information here is showing us is basically that where the lime is up here is not where it's needed. Conversely, where we need the lime is not where it currently is, right? So I think that kind of hopefully provides a bit of extra information about what's happening or what's likely to happen in the future, given the amount of lime that we're still measuring in the soil profile. So if we turn now, as Josh has already shown you, you kind of stole my thunder there, Josh. I did a similar analysis on some of the sites up on the Eyre Peninsula. So briefly, this is the kind of pH history of these sites. The little star indicates a liming event. So you can see some have only been limed once, some have been limed twice. The rates of lime is different depending on the different sites. And you can kind of see how that's increased the pH following a liming event. I'm not going to spend too long dwelling on this because I'd go into it a little bit more detail in a second. But this is the same information that you saw previously from Josh's slides. So this was just the pH of each of those sites in 2023, which we can see if we're looking where the 5.5 is really, or actually no, most of the sites, at the surface, kind of at 5.5 or above. Below the surface, only 2 of the sites have achieved that 5.5 further down into the subsoil. If we look at then where the lime is in each of those soil sites, similar story as we saw up in the mid-north, most of that lime is hanging out in the surface of the soil. But I suppose, or differently from what we saw in the mid-north, if you look at the x-axis of this scale, it's like 0.1%, so it's hardly any lime left. And if we present that information in a similar way to what I did with the previous sites, you can see the amount of pH increase that's possible, given the amount of lime that we were detecting, is quite minimal. So really, you're not going to get much more of a pH increase at really any of these sites. So a reapplication of lime, certainly at the sites that still need quite a significant pH increase, would be recommended. And that's not necessarily a piece of information that's available if you're only looking at the pH. You kind of need to know how much lime is left in the system to really be able to kind of know when to re-lime, I suppose. Now, I'm just keeping an eye on time. We're probably cutting it a bit close to the end now. I've got, we can kind of go by it through it case by case, or if you're interested in kind of checking in with me about this, you can send me an email and we can chat about it a bit later on. What do you reckon, Amy and Josh? Should we kind of wrap it up now?
We can. Do you have, and Josh, you might know here, do we have any sites that are close? No, we don't really know. That are close to Billy's place. I was going to say, put it in a little bit of perspective for him.
There isn't any. Sorry, the ones that were chosen were just ones Brett and I were able to sample just before Christmas. So, yeah.
That's okay. We can leave it there. I guess we can open it up to questions, though. We have got a few minutes for that. So, Debbie and Billy, do you have any questions? This is a prime time and chance to ask anything, not necessarily in relation to the presentation, but anything soil pH related.
And I suppose if not, I can just quickly kind of do some trends on this data rather than going by it, through it case by case. So you can just kind of see just a few things to comment on here is that the sites that have only had that one application of lime, there's no lime left basically. So in all of the sites that have had more than one application, there is some lime left. I mentioned that it wasn't a whole lot, but you're seeing that, yeah, kind of makes sense. The more lime that you're applying, the more there is in the system still. And I think interestingly here as well, something that is kind of this graph here is showing is that there is more undissolved lime further down the soil profile in this Cockalichi site, which is a coarse sand. So we would expect to see more lime movement through a coarser texture soil. Kind of to Josh's point, these water moves freely through soil, through sandy soil, as does lime, as do most things. So you would expect to see more movement in those sandier soils as opposed to a heavier soil. And then just one more thing that I think we discussed at our acidity forum on the EP, and you've mentioned here, Josh, was when that pH at the surface gets too high or gets kind of over 6.5, there's not a whole lot of lime movement. And I'll just quickly skip to this site here, because I think this site kind of demonstrates that point that the two lime applications, like the last lime application happened in 2016. So that's, what is that, 7 years ago now? And so that's quite a long time ago. You would expect that all that lime was only 1.2 tons in at that timeline. You'd expect that would have kind of disappeared by now. But I think the reason that we're still seeing some lime in the surface in this case is because that surface soil is already up above 6.3. There's kind of not that acidity to dissolve it and get it moving. So I think that kind of just highlights that case of like you asked that question, Billy, about applying 10 tons at the surface. If you were to just apply a big chunk of lime to the top, you'd get a huge increase in pH at the surface, but not a whole lot of acidity would be moving down the soil profile. And these results here just kind of support that a little bit. That was just all I wanted to say on those sites.
No, thank you very much for that, Ruby. So yeah, does anyone have any questions? Otherwise, it would be great if you are able to jump on, and I'm just posting the evaluation link in the chat, and it would be great if you're able to jump on and fill that out. It's very quick, I promise. I think it's got 6 questions. So
Billy's just got one question, sorry.
Oh, you have two. Take-home message for the lower EP gravels, particularly where deep ripping or deep incorporation is difficult, is to add 2 to 3 tonnes a hectare of lime every 3 to 4 years in hope of attempting to increase subsoil pH.
Yeah, that would be, like I said, the best case scenario is that's what happened. But it's also not always a given if you're not getting that movement down the profile. But yeah, that 2-3 tons every 3-4 years, that's what's the best case scenario. That's what's happened, and it has moved down the profile. But yeah, yep.
Does that answer your question, Billy? I hope so.
It's the tricky. The big unknown is those gravels. Sometimes some are more porous than others. It's the big unknown. So it's certainly a really good place to start with those sort of rates at that sort of intervals. And then the trick would be to go back and have a look at what's happened. But from the work that Ruby's shown and the monitoring data, if you can get those gravels and sands to get the lime to move down, that's a really good scenario. Yep.
No worries. Thank you for that answer, Josh. Much appreciated. Like I said, I have popped the evaluation link in the chat box, and it was great for you guys to jump on and join us today. We will be emailing the link of the recording out, so you can rewatch it if you'd like.